Okay, I think we're ready. We continue with the next talk. Our speaker is Martin Parm, and he's talking about monitoring at Spotify. Have fun.
Good morning, and welcome after last night. Hope you enjoyed it as much as me. How many non-German speakers are in the room? Show of hands. I enjoyed the music as well, but had you any idea what she was talking about? So, I'm going to try something I haven't tried in a while. I'm going to give a non-technical talk. This is going to be probably the least technical talk you'll hear today, probably also yesterday. It's going to be probably one of the most boring slide sets, because I want you to pay attention to what I have to say. I'm not going to show you a lot of screenshots. I'm not going to show you a lot of demos. I'm not actually going to show you any demos. I'm not actually going to talk all that much about technology. I'm going to talk about people. And I'm going to talk about the story of how monitoring at Spotify came to be what it is today. Because we felt we learned a lot on the way, and hopefully someone else will learn something too. And the people part is interesting, because when we go to these talks, we hear about new systems, new solutions, things at scale. That's fantastic. And you go in the corridors, and you hear people talking about people. The same old conversations with management that won't allow you to install the new shiny monitoring system. Your developers that don't understand why monitoring is important. And the thing is, monitoring is a tool. It's not a goal. It's not a thing in itself. And it's driven by people. And no solution is really better than the people serving. So let's talk about the people. So a little bit about myself. I'm living in Sweden, but I'm actually Danish. I'm 36. I'm not as old as some of the old-timers I've met. I'm not the youngest one either. I'm in this weird in the middle. I have a degree in computer science from Copenhagen University, where I also had my first operations job. It's probably a story you heard before, managing the university network. I joined Spotify in 2012, working with infrastructure. I joined monitoring in 2014, and for about a year I've actually been the product owner for monitoring. Up until then I was an engineer. So let's see here. So first a disclaimer. I'm going to mention a bunch of software, because software is part of the story. I'm going to say positive things and negative things. This is all in the context of our journey, our story, our needs. So I'm not going to advertise for any piece of software, and anything I'm saying bad is not necessarily dismissing any piece of software. But it's easier to say something sucks than saying this particular version of this software did not scale for our particular use case in this point of history where we had these problems, because then it would be a very long talk. Another thing, I'm going to talk about what we're doing. It's not a sales pitch for our solution. Keep in mind that our solution is built for our needs. We share it with you because someone might find it useful, but don't take it as, well, this is the way you do it. So, Spotify. Let's talk about who we actually are and what we do. So we're music streaming service. You all know that, hopefully. But more importantly, we're actually music discovery as well. It's very little part of our infrastructure that has to do with actually serving you the music. Most of it has to do with telling you which music that you actually like before you know it. We have a number of clients, we have a number of partner integrations, all these nice numbers, 20 million paid users, 75 million daily active users, giving back so much money. These are numbers, official numbers, they are from June. And the point of this is just to say that we serve a lot of users all the time. We generate a lot of traffic, we have a huge system. That's it. We are organized in 4 major tech offices. We also have small sales offices around the world, but technology is physically actually in tech offices. We have around 1,500 people worldwide. Around half of them work in technology. 100 of those people, around 100 of these people, work in infrastructure, building infrastructure. So a little bit of math, that's roughly 100 people building infrastructure alone, and then another 600, 700, 800 building the rest of the technology. And 6 of those engineers are building monitoring, and just monitoring. We have 4 physical data centers in the world. We have around 10,000 servers. Those 10,000 servers is serving the music service. It's a microservice infrastructure, meaning that we have a large number of tiny services that does one thing very well, and these services should hopefully be able to fail independently. So, if the playlist service fails, then sure you can't browse your playlist, but you can still stream your music. If the metadata service fails, well, maybe you don't get the album cover for the song you're listening to, but you can still hear it or add it to your playlist. This is simple consequence. When you have something that is rather complex and rather big, then statistically some part of it will always be broken. So you need to manage dependencies. But it also means that, yeah, we have more than 1,000 different types of machines in this data center. Every one of them doing something unique. And it's mostly running Ubuntu Linux, just for reference. We're running with a model called ops and squads. I'm going to talk a lot more about that, which basically means that the feature teams that develop these microservices are responsible for operating them as well. So you have a team of developers, they develop something, they are in charge of installing it, figure out what they need capacity-wise, they're in charge of their own monitoring, they're in charge of being woken up in the middle of the night when something is broken and fix it. And so monitoring is not monitoring team monitoring everything, it's monitoring providing monitoring as a self-service product for these teams. We currently have 2 monitoring systems. And the most interesting one of these monitoring systems is the Timeseries database that currently has 100 million Timeseries in it. Which is somewhat big number. Other companies have more data than us. But more interestingly, how did we get to there? So it started back in 2006. I'm going to go briefly over the first bit of the history, both because it's not so interesting, but also because I wasn't actually there to experience it. So this is me having talked with some old-timers in the company. So just remind you that this was a different time. No cloud computing, no smartphones, and cloud apps was only really starting to come out. So it was mostly like PCs and laptops. The internet was a thing. The rest of it came later. Back then, some engineers got the idea to start a music streaming service. So they got together and that's actually a little bit too quick, that one. Got together and started building this service. And of course, these people were trying to build everything at once. And so monitoring actually came pretty early in the process. But what's interesting is how the awareness in the company came to be. Because the company at the time, we were like talking 20 people. So it wasn't like teams having meetings. It was the company having a meeting. The whole company could sit together and have a meeting about the whole company, which is ridiculous today. And so back then there were actually very good meeting notes of those meetings, what people were interested in. And interesting is that the first mention of a monitoring system was not when someone said, oh, we should probably monitor this. It was not when someone said, oh, so what solution should we pick? Someone just picked it and installed it. The first time that the company outside the person starting the monitoring system got awareness of monitoring was monitoring fatigue. People didn't care about monitoring until they started spamming them. You probably heard this before. Anyway, so the first graphing system we had was something called Citement. It was an in-house built system. It was basically Moonin, but with a custom front end. Moonin, you probably know Moonin well enough. Pool-based solution, writing to RD files, multiple resolution is created by writing to multiple RD files, and so on and so forth. The nature of the system was that it generated a lot of static graphs. The resolution wasn't that high in about 5 minutes, and it was one dashboard for the whole company to look at. So everyone working on the back end will look at the same graphs, and the most interesting metric there was back-end request failures. So we have a microservice infrastructure where your client talks to something called an access point, and the access point will then talk to all these services, and when these services start to fail, that would generate a back-end request failure. And we count those, and when those start going up, boom, something's probably broken. But everyone was looking at the same graphs. What about alerting, though? I talked to Emil, was like the third person in the company, and this is what he said. The very first alerting system we had was literally a guy sitting looking at graphs. Not because someone had told him to or paid him to, but because he was very interested in making sure that everything worked, and he apparently spent a lot of time in front of his computer. So he was looking at graphs all the time, and when something was wrong, he would call you. This is how it worked. Not very scalable, of course, but hey, we're still here. So the first steps with alerting actually happened after our launch. We launched in Sweden and UK first. The first time was scary because it was all new, but some things were easier to control because the service actually launched as an invite-only service. So we could scale up our traffic when we had the capacity. So we had capacity for more users, we send out more invites. A luxury that you don't have once you go live. But of course, this looking at graphs didn't work, so we installed Zabbix. Alerts were sent. We had a classical division. We have some people who were mostly operations, and some were mostly developers. There was a strong DevOps culture where everyone helped everyone else, so it worked. But the chain of command was alerts went to operations. Operations would figure out which developer to involve, and then the debugging would start. The alerting rules were not very good for various reasons. So other common sources of alerts were actually users complaining about something not working. That actually led operations to at some point set up a permanent Twitter search for Spotify is down, which is surprisingly effective. So effective that our customer service have actually run with that idea, and our customer service department actually have several really clever systems built in to monitor social media for people complaining about Spotify. It really works. And when you think about it, it's actually really good data because you can measure all sorts of things in your system, but the source of truth is that if your customers are having problems, then you have a problem. It's some of the best data you can have. But most of the time you want that data before it hits your users because, well, users get angry. Fast forward a little bit. 2011, 2012, where we start using ops and squads. So what happens is that around 2000, 2012, we start being successful. We launch in the US. We have the money, we have the power, we want to go places. So the company scales up massively. We hire in hundreds of developers in a few months. If you have ever tried that kind of scaling organization, it is scary and it is rather painful because it has a real effect on your culture. When you hire 1 or 2 people, you can tell them how you work, and they will be influenced by your team. When all of a sudden you hire in brand new teams, whole new teams that have not been in touch with your old teams, they bring a new culture. And one of the things that we had was we actually had a pretty good DevOps mindset beforehand, but we started hiring a lot of developers who didn't have the operational experience, who had not been operating their own servers, who were brilliant developers, but they hadn't seen that side of the business. And we became more focused. Developers were doing development, operations were keeping things alive, and a rift between developers and operations people starting to emerge. Pretty bad situation, actually. So development sped up. We had lots of new teams. All these new teams was like spitting out new microservices left and right. The product as it was grew when we could do a whole lot of things. But of course, when you develop this fast, that not everything is necessarily high quality, and even if it is high quality, it's not without problems. So stability became a problem. And who was dealing with stability? The operations team, who had not been part of the development. And when you're keeping up with just a few teams who are doing development, that's fine. But when you have brand new teams that you didn't even exist, all of a sudden spin up a service that you have no idea what it's doing until it wakes up in the middle of the night, you start getting angry operations people. Service ownership was often unclear. Figuring out, well, you found this machine you had no idea existed, so who owns it? Who should I wake up? That was a problem. And yeah, basically, at some point we realized that having a classic SRE team did not scale. It simply didn't work. Not just because of the size, but also because of the complexity. If you have a big company that does one thing, that probably works just fine. But we had a mid-sized company that did thousands of the things. So the situation was we had big incidents almost every week. So the business was pretty unhappy. We had constant panic and firefighting, so the SRE teams were unhappy and rather tired. And so to sort of stop that, we had all sorts of little policies and checkboxes and things we tried to improve. One thing, for instance, don't deploy on Fridays. You heard that one before? It's actually really good for keeping your service stable, but developers who all of a sudden have a 4-day week for deployment instead of 5, they get angry because they want to move fast. So everyone was unhappy and angry at everyone else. We need to do something about that. We came up with ops and squads. It has been dubbed a few things, ops and squads. It's basically DevOps mentality boiled down to the way we run teams. And the idea was, okay, stop it. We can't have an operations team. Let's spread out operations in the teams that actually build the services. So we put them in charge of their own capacity planning. We put them in charge of their own configuration management, deployment, monitoring, alerting, defining SLAs. I mean, when you don't know what a system is doing, it's very difficult to know if it's critical or not. So let the teams do that themselves. And managing their own incidents. That was the idea. Of course, when you go out to developer teams and say, by the way, we want you to do everything you do already, but also be operation engineers, they're not. We needed to frame that slightly different. But one of the benefits of this, all of a sudden, when you do this, you have a scalable organization. Because every team starts operating independently and making local decisions that make sense for them. Basically, every part of the organization started operating as a startup again. Faster incident solving, because most times when something breaks, you need to talk to someone who knows what the system is doing. Sometimes you're lucky, you can just restart it. But a lot of the times you need inside knowledge. So getting the right person in front of the computer faster makes incidents go away faster. Accountability. If you make something that breaks in the middle of the night, you're the one waking up. That gives people a strong incentive for fixing it. This sounds like torturing developers, but it goes beyond that. Because if your team builds something that breaks in the middle of the night, so your team members get woken up in the middle of the night, so they are demotivated, tired, and not performing, then your product owner all of a sudden have a strong incentive for giving you time to fix it. So this actually works. And autonomy. All of a sudden, we could remove this rule. Why not deploy on Fridays? You can deploy on Fridays. If it doesn't work, then it hurts you. So make your own decisions. Talk about it in your team. Is this a good idea? But there's no top level that says you cannot do this. Just know that we hold you responsible for what happens. But this comes with some human challenges. Because that means a lot of engineers need training. But they don't need a full set of, a whole new education. They don't need to be complete operational people. They don't need to know all the details. So finding out exactly how much they need to be able to do their job is a challenge. And then you package the rest. Developers need autonomy. So we want to give power back to the developers. They make their own decisions. Well, even the best developers make mistakes. So make sure that we know that these mistakes will happen and how to deal with them. And so one of the things we do there is trying to limit impact. And so in the context of monitoring, which is why we're here, that means that your developers need to understand enough about monitoring to be able to do their own monitoring, but they don't actually need to learn about the monitoring pipeline. They don't need to know about how you scale monitoring. They don't need to know about all the nitty-gritty details behind the scene. But they do need to know about good monitoring mentality. And so we needed to start providing infrastructure as a service to our developers, giving them enough tools to be able to be self-sustaining. So the classic operation team was actually disbanded, and our operations engineers and different tools teams, because we all have also spun a few of these, all became what we have today, which is IO, our infrastructure team, or infrastructure organization. Actually, it's multiple teams, 100 people, and we went from solving people's problems to making tools that solve problems. So teaching and self-service became the main focus. My old boss, the guy whose job I now have, said that it's probably the smartest move that we have done. Probably one of the smartest moves we have done, at least within operations in Spotify. Because it meant that we could get ourselves out of this place where everyone was unhappy and everything was breaking. So I'm going to tell 3 tales of failure from this time, because not everything was rosy red. But after talking with you yesterday, I think I need to clarify something. I also say in the bottom it says read learning opportunities. This actually has to do with Spotify culture. In Spotify, we actually talk a lot about failure as a good thing. So if you visit a Spotify, if you hear people talking about, oh, this failed and that failed, and we learned this and we learned that. And that's because we actually encourage failure. Not as in, oh, go and break something just because, but move fast, fail fast, learn from it, and then move on. So we talk very positively about failure, but I realize if I just tell these stories as, oh yes, we failed horribly at this, then we might miss the point. The point was that we learned something useful from these experiences. So the first one was Citement 2. Okay, so Citement 1 obviously didn't scale. Mooney didn't scale. And looking at the same dashboards, everyone looking at the same few numbers didn't scale when the service became very complex, because we wanted teams to worry about their part of the service, not the entire thing. The first, actually, we had this team, back-end infrastructure team, that was formed before the whole ops and squads, and they were actually the first infrastructure team. And they were tasked with solving 3 problems: log delivery, and monitoring, and alerting. And those 3 things were put together because, well, log delivery and monitoring, well, that sounds similar. If something fails, you go look at logs, and then you probably can do monitoring based on logs, and it sort of fits together. Problem is that we also use logs for business-critical data. So what we do is we gather all the logs from all the access points, process all the things that we have collected about how people are behaving, and we use this both to generate reports to the music business about how much we owe them, but also to figure out, so what should we suggest? All our business critical data is coming from log as well. Anyway, we started developing Citement 2. We didn't really think about doing anything else but make it scalable, so it was meant to replace Citement. The first Citement, it was based on Mooney still, because we didn't really want to do all the migration, but we tried to put in a Cassandra backend and a much more powerful frontend. This did not go well. Not because the product didn't work. Actually, it sort of did. The problem is that Citement 2 and this team were developing this in isolation. They weren't actually working together with the operations team that was still in place. They were not really talking with the engineers. They were building something for a monitoring team. So they ended up building a feature set that worked, but wasn't really what people needed to do the job. And a priority collision. Because when a team have multiple priorities, and one of them is breaking for different reasons, and when our log delivery failed, we could measure and reason about a business value. When we cannot generate reports to the record labels, when we cannot fuel our suggestion backend, then we are hurting financially. If the monitoring system isn't working, well, we may be fine. It's much more difficult to reason about the financial side of that. So log delivery was always more critical. So most of the time went into doing log delivery. So what we learned from this was basically, yeah, you really need to talk to your users, but if you want something done, you also need to make sure that the team has to do it don't have this priority conflict. You want something to succeed, you build a team around it and has that as the main priority. This is not the only place in the company we've seen this, by the way. We've seen this many times. We're still making this mistake every once in a while. The next thing is we tried to build a new alerting system. OMG, oh my God. This time we thought we had learned. Okay, so it was a new team. We had learned that we need to talk to operations. We need to include our users. So an operations engineer was assigned. And the guy who built this, well, the guys who built this are very technically skilled, especially the guy who spearheaded the development has an analytical mind like no one I've ever met. And the operations engineer that was assigned was a superstar as well. So how will this fail? And actually, it went really well. They built this OMG thing. It was a streaming event process similar to Riemann, if anyone knows that. You send a bunch of events to it, and you write rules, and out comes alerts. The initial development went super fast. They got something up and running, they sent it in production, they started talking to teams, everything was fine, a few teams started adopting it. This was what a rule looked like. I tried to reformat that a bit. It doesn't get much prettier. The problem here was that they decided to go with a language called Esper. If you haven't heard about it, then I'm not surprised. I hadn't either. It's a very small language. It's built for stream processing, and on the technical side, it's really good. It actually is. The problem is that it's very, very difficult to read and reason about, and for most people, it's very difficult to learn. The learning curve was very steep. And why was this not caught? Well, the guy we have assigned to help out, the operations guy, he had the same analytical mind. He loved Esper and saw nothing wrong with it. But of course, people refused to adopt this. And the third one, Monster. I'm going to speed up a little bit. Citement didn't work. OMD didn't really work. One of our architects decided that, how difficult can this really be? So he started from scratch. He actually used the Mooney data, but then he built an in-memory Timeseries database. And he actually managed to put together a prototype in 2 weeks, and it worked great. It was blazing fast. And he talked with operations, so people loved it. So yeah, he turned the Mooney model around. He was now pushing data from the individual hosts. And so Citement 2 was halted. Citement 1 still existed. But this actually seemed like a good success. I'll get back to why that was actually a failure. Because that came later on. It started out looking like a success. So we now had learned our mistakes. If we need monitoring to be good enough to these teams that we expect to run their own services, we actually need a dedicated monitoring team. So we put a team together, and they were tasked with providing monitoring as a self-service, rather than just solutions. We inherited Monster, this new system that was built, Zabbix, and OMG. And the programmer at the time was very clever. He realized that we had too few people to tackle all the problems at the same time, so he made some quick calculations. Obviously, this thing with an in-memory database does not scale because you run out of memory. But it was good enough for now. He calculated that Monster would probably be able to survive around a year until we have found something better. So let's tackle alerting first. We replaced Zabbix and OMG with Riemann. It's another event streaming processor. And it's written in Enclosure and has Closure as its language. It's a little better than Esper, but most importantly, it actually have a community around it, so a lot of tools exist. And so we built some libraries with helper function. We had namespace support, and we made unit tests. So not only could you write rules for your alerting, but you could also write a unit test to prove that your rule does the right thing. And we ran those unit tests every time we changed something, which meant that, we built a web front-end as well. That was less interesting, actually. That we could now write rules that look something like this. If you don't like the Lisp-like languages, it's still a bit ugly, but at least it's readable. It was widely adopted. Riemann was actually a success. Teams started writing a lot of rules, started getting their own alerts. Riemann was actually is a true self-service system, as the rules live in a Git repo that everyone has write access to. Now, having 400 developers, engineers, messing around in your monitoring system, if it isn't built for it, it sounds scary. But this system was actually built for that. That was exactly why we made namespacing support. So every team has its own namespace, and they only mess around with their own rules. And we don't do code reviews on these rules. We rely on the unit tests that the same developers are writing to ensure that they don't break things for each other. was still kind of a failure because many engineers don't really like to write things in Enclosure, especially not Java developers. That actually became a complaint. But we considered it a success because we actually had something that worked. So we went on to pretty graphs. Now that's where the things became a little bit more muddy. We started looking at collect-D and graphite. And at the time, with the size of the company, the size of the complexity of the things, and the way we wanted to operate a monitoring system, sharding and rebalancing was an issue. We know that the Cyanide backend has probably solved some of these. I haven't actually tested it. But at the time when we looked at it, this was not a good solution for us. And we started looking around because there wasn't actually any really good solutions. Not really. Now, one of the problems was that Graphite and other solutions were still using these hierarchical namespaces. So you define your metric descriptively with like a very long key name that contains all the data. But when you want to start slice and dice those metrics, it actually becomes kind of difficult. Again, probably not a surprise to those of you who have been following the latest development of other tools. So the solution was Metric 2.0. You've probably all heard this. Have anyone here not heard about Metric 2.0? Really? Okay. Brief slide on the idea of Metric 2.0. The idea is taking these very long names and breaking them down into tags. So rather than having a long name that contains the host name, you actually have a tag saying host is this. But you can also have all sorts of other things like what does this machine do, what are you measuring, which network is it part of, yada, yada, yada. And the point is that selecting the right metrics for aggregations when you have broken the metrics down like this is a lot easier. So a bunch of the bigger time series databases are actually moving towards this kind of idea rather than the long hierarchical name. This becomes especially important when you want to caring about single machines, but actually want to start selecting machines across other dimensions like what switch are they connected to and what service are they running. So we knew that this was a muddy ride. We needed to have quick adoption because we really needed to have people own their own service, but we also needed to have the flexibility of trying things and throwing them out. So that was actually a problem, and we can't ask our engineers to migrate every time we get a new idea. Then your team starts slowing down because they spend all the time migrating and they become pissed. So we came up with the idea of having a small API. We wrote Fast Forward. Fast Forward is a simple idea. You have a small daemon running on your machine, and you tell people, this is where your metrics go. This is where your monitoring data go. And they can throw metrics and events at Fast Forward, and then something magical happen, and it comes out as alerts and graphs in the other end. And where metrics and events actually go is something that you have control over and configure in Fast Forward, but your developers and your teams that are using this do not have to worry. This is your contract with your team. We can change everything else, but your things still go to Fast Forward. And so we end up with a system that looks like this. And we get the flexibility to play around and change things in this pipeline without forcing our users to migrate all the time. Yeah. So we looked at a bunch of solutions. I'm not going to mention them. They are the links to them in the bottom. Point was, some of these solutions that are good contestants, they simply didn't exist. Other of them were not good fits at the time. So we were kind of at a loss. We came across KaiosDB. It looked promising. We installed it. It sort of seemed to work. It had problems with queries. But we thought, hey, we can work with the community. Except timing. When we started using it, the two main developers got snatched by DataStax, the company behind Cassandra. And all of a sudden, they were working on Cassandra and not this. So development halted. But we needed a solution. So we started building Heroic. Actually, we never set out to build our own time series database. Heroic started as an alternative query engine for Cassandra, basically because we needed a query engine that didn't fail all the time, and we couldn't get in touch with the CarsDB developers. So we started out building this query engine, and at some point we realized, well, this is going nowhere, we might as well finish the job. So we switched to our own schema and replaced all bits of CarsDB, and now we have Heroic, a time series database, built on top of Cassandra. We also started having a lot of metrics, so we needed to have more than just the in-memory model that CarsDB had, so we started using Elasticsearch for indexing the time series just so we can find them. So back to the monster failure. Now we had a solution, we had a time series database. The problem was that anything you build that has a proper backend will be, at least to some degree, slower than something that runs just in memory. So from our user's point of view, Monster was the shit. It was blazing fast, it worked. And whenever it didn't work, whenever it broke hard, it crashed. And who got woke up? Us, not our users. So our users got the glory, we got the pain. And so convincing our users that we wanted to switch to something else was actually very difficult. So you can actually have a product that is, even if it doesn't scale, even if you can explain that it doesn't work, but when it does work, your users love it, it's very difficult to migrate away from. It's a human problem, not a technical one. Yeah. It actually lasted until a few months back when we finally said to the last users, oh, we don't care, we shut it down now. And to give you some idea about how painful it was running Monster in the end, in the last 6 weeks of the lifetime, it alerted us, as in woke someone up in the middle of the night to be restarted 51 times. That's horrible. Sorry? I have no idea. This has crashed a lot. Final story, and then I'll go to questions. Now we had pretty graphs. We had our alerting system, but we also needed graph-based alerting. The problem was that actually alerting started to become a problem again. Once we have solved graphing, alerting that we thought we had solved became a problem again. Riemann became more difficult to scale. You probably can, but in our case it was difficult. But more importantly, complaining about closure became one of the #1 complaints that we heard. Engineers did not want to write complex rules. They kept saying, oh, we want something simple. And at one point, actually, one of our teams dropped our monitoring stack and went with an external vendor. And rather than shout at them, we went to them and said, okay, so you try this external vendor and you tell us what you think. Please let us learn from this. What is that you like? And what turns out was that what they really liked about this was, apart from having easy metric collection, was also that a lot of their use cases were actually, oh, we have a graph and we set a threshold, and when it goes above, we want to alert. And we don't want to write any code for it. We just want to have the line. So we said, okay, we can do that. So we built graph-based alerting into our own system. Simple thresholding. You had the very same graph that you were looking at. You could have an alert that goes either above or below, or missing if the data wasn't there. And we did we integrated directly in the front end, so there was no code. It was just you making a configuration that kind of looked like this. So you had the very same graph you had, but now you could make an alert definition and say, if it goes above this line, alert me, or above this line for so and so long. And we thought clearly there's use cases for this, but not a lot. But the result was that our engineers, when we made this, they started mass migration. People moved out of Riemann as fast as they could. We didn't ask them to. They just did. They came in and deleted 100, sometimes thousands of lines of Riemann code that they had written themselves because they didn't need them anymore. So it doesn't matter that we said, oh, we probably want something more clever than just a threshold. The reality was that our engineers who were running this wanted thresholds, and this gave adoption. And so this was actually fueling adoption quite a bit. Because, well, many monitoring problems can indeed be expressed as a simple threshold if you have a powerful enough query engine and you collect the right things. So what we saw was a lifetime of Heroic. The number of time series that we were collecting, the amount of data we were collecting exploded. More or less overnight, because people all of a sudden had value and it was easy to use. And we're currently collecting around 10 terabytes of metric data worldwide every month. And this is with our current rate. But one of the lessons that we have had from this is every time we make something easier and better, more people will start using it. So scaling is not over. And so our current pipeline actually looks like this. This is what our magic cloud looks like right now. It's still fast forward, because this was a very good investment. So people send stuff into fast forward. It goes into Riemann and Heroic, and we get alerts and pretty graphs. We have both systems running, and this is what it looks like right now. But the system that people use the most, love the most, is actually our time series database. We've actually open sourced it just yesterday. We've been working for a while because, as I said, fast forward it was meant as a good idea, so that was developed in the open from the get-go. But Heroic was never meant to be its own product. It was a patch solution for something that we hoped someone else would fix. And so by the time we had a finished product and said, "Oh, we're going to open source it," then we had all the extra work that comes with that. So it only happened just yesterday. We have more components; they're probably coming out soon. But this is the one that I can tell you is actually out there already. Now I have more slides about what we have learned so far, but I would rather take questions so we direct it to what you're interested in hearing about. So, unless there are no questions, then I just continue.
Yeah.
Yeah, hi. In the beginning, you mentioned you have 10,000 physical servers.
Yes.
What kind of? Are they custom built or something standard hardware or whatever?
It's a mix. Today we have aligned our server infrastructure as much as we can. So we are, I can't even remember what brand we're running, but we have, rather than trying to build, say, for instance, deployment systems that can deploy everything, we have a limited number of types of machines. And so when you're a developer and you want to deploy your service, you deploy, say, a high CPU machine or a high IO ops machine, if you know that you're doing something with a database. So that's what we're doing. This was not always the case. I'd say around 2010, one of the major complaints were that we were switching vendors left and right. And so at one point, we probably had more or less every vendor in our server room. And that's not a good idea when you want to manage a lot of machines.
How did you make sure that you learn from your colleagues in different departments about things they want? Do you have some kind of communication? What do you use? How do you make it?
Good question. The general answer to that question is, of course, that you make sure to pick up the learnings when they happen. This is a general pattern that we have all over Spotify, not just with monitoring operations. When we have a major event or a failure of something, we do something we call a post-mortem. It's basically a big meeting where anyone who had a stake in it or were involved with it will sit down and go through, okay, so what exactly happened and how do we, what was there to learn from it and how to make sure that it doesn't happen again. This is actually how we handle most of our backend incidents. Whenever you have an incident where you actually have downtime, you have a post-mortem in your team. The idea being there that having a failure is not a problem. Things fail, things break, things you didn't know about. Maybe you have a bug. Having the same failure twice, that's stupid. So figure out what went wrong afterwards. And that happens on bigger things as well. Like when we do a big launch, and after the big launch, we realize that this was a horrible experience for the developers, or we missed a deadline, or this was totally not what our customers wanted. What did we miss? We have a postmortem about that as well. The second thing when it comes to building infrastructure is once you know what is the right thing to do, you can both teach it, but you can also build tools and golden paths to sort of push your users to do the right things. Otherwise, they will be clever and do all the wrong things that you yourself already did, but now know better.
You seem to do a lot of coding for your monitoring solutions. Is this something that your core monitoring team of 6 is doing, or are you just speccing it and passing it out to the dev teams?
The infrastructure involved in the monitoring system, so Riemann and all the libraries we built there, Heroic, all of the things we built there, all the things that we don't want our feature teams to be aware of, they shouldn't care about, that's something that we in a team of 6 are building. When it comes to defining alerting rules or setting up dashboards and all these things, that's what the individual feature teams are doing. And what we're seeing now is also that when they want to move faster than we, a team of 6 people, are capable of, they're asking us to actually make our monitoring solution, add APIs to our monitoring solution, so they can start building the tools themselves that they want us to build, but we don't have time for. We don't have, for instance, dashboard templating yet, and so everyone is building their own dashboard from scratch. So one of the number one feature requests from a bunch of teams is, but just give us an API so we can inject our own dashboards and we'll build the templating system for ourselves. When you get to the point where your customers are doing your job and building your own things, you know you're on the right path.
Just a quick question. I've been looking on your blog post and on the website for Heroic. Yeah. What is the license?
I think it's a Apache license or something.
The reason I ask is I work on a project called OpenNMS.
Yes.
And we have a Timeseries database called Newts that's built on top of Cassandra.
Yes.
And because I'm all about the open source, I'm looking to see if there's some way that maybe we can work together between Newts and Heroic. And so we're Apache licensed as well. So if it's Apache, I think there might be some good synergies there.
Well, the easiest way to find out is actually to just look at one of our source files, because one of the, for developer painful things, but for company sane things we have is that whenever we open source something, we require that the license is as a header in type of every single source file. So open up a source file and it will be right there. It's an Apache license. Okay.
So storing 10 terabytes of matrix data is a very impressive number. What kind of storage are you using to store that data? Do you need SSDs so that it's fast enough, or are you using internal disks, or is a network attached storage enough for storing that amount?
That's where it becomes a little bit interesting. We have grown beyond SSDs. The Cassandra clusters that we're running right now is running with a particular type of storage that's called FusionIO, if anyone heard about that. Basically, FusionIO is a gigantic flash drive, and it's super expensive. This is also one of the reasons why we don't think we're done developing, because in the beginning when we wanted to build monitoring and it just needed to work, it was important for the company that we moved fast. So we're basically, yes, throw hardware at the problem until it works. So we did. And it does work, and the value we get out of it. Don't get me wrong. The value we get out of having the solution at our scale far outnumbers the cost of the hardware. But there is a threshold, because we currently have unlimited history. So we keep scaling our Cassandra clusters. And last time I asked for doubling our London cluster, our chief of operations, he looked kind of funny. But monitoring is a difficult thing, because metrics that you're collecting, they have values 2 times. They have value when you collect them, when they're true, and you have alerting rules that look at them. Then they're valuable for you. But anything you collected might also be valuable when you want to go back and see what the fuck happened. But it might not be. And when you're collecting tons and tons of data, there's a lot of spam that you will never use. But you have no idea what it is that you don't want to use. And our experience right now for our situation is that it's actually better to just give developers the ability to collect a shit ton of data and sort it out and deal with it, rather than trying to optimize for cost early on.
Thanks.
More questions?
Do you guys have a kind of fixed pattern sharding your Cassandra clusters? So do you, do you try to generate the data locally and just collect them for the dashboards from the locations, or?
No. The system is built around the idea that the monitoring system needs to be extremely robust. When everything is on fire, the monitoring system should still be alive. Otherwise, it doesn't really tell you much. And so we try to get the monitoring off the host as quickly as possible, because the host might die. We run with a replication factor of 3 in our Cassandra cluster right now, so we can lose nodes. And we run with a Cassandra cluster we run with like a copy of the infrastructure per data center. Because the idea is that we should be able to lose any one data center, and the rest of the monitoring should just keep working. And if it's just network that goes out, even if you cannot access and nothing goes and you don't know what's going on inside your data center, when network comes back, we want all the data to be present so you can inspect what happened while you couldn't access your data center. So local Cassandra clusters in our data center, high replication, and basically anything we do is about scaling horizontally and having high replication, both to be able to handle the amount of data and the amount of requests, but also just to be able to lose any one bit. We don't want to have a single point of failure anywhere.
Okay.
Hey, are you also using the same system for monitoring of your network, for example? So not just pinging, also for deeper layer 2, layer 3 monitoring?
The monitoring solution I've been talking about here is mostly focused on backend. We have different monitoring solutions for our front end. The people who run our website have gone with a commercial solution, which is good because it's focused on ours is a generic solution. Theirs is a solution focused on good monitoring and good debugging for specifically websites. So it's a much better solution for them. Network have their own issues. They're actually building some monitoring solutions right now. We're assisting them with our knowledge, but their data model doesn't really fit into what we're doing. Yeah. And we actually have a similar situation with our analytics pipeline. Again, we're helping them with best practices and we're helping them building that, but the data model looks different. Our system is tuned for massive amounts of very simple data. You measure things, but you measure millions of it. Data pipelines, you have very few data points, but you want to know about dependencies. So if the data pipeline breaks, you want to know, so did it break because something else broke, and who else is affected, and where are deadlines, and all these things don't really map into a time series database. And rather than trying to mash everything together, we try to share knowledge rather than technology.
Okay, one last question.
Hi. Just a short question. So with the current solution running on Heroic, you kind of lost the ability to run unit tests against the assertions which you have. Is there something which you plan to bring in, or which you even have to do it, or to expand it?
Not really. Unit tests made a lot of sense when you write your rules as a piece of code, and you're loading on an incoming stream of events. Also metrics, but you have a piece of code you're testing. Because the piece of code you're doing, depending on what you're looking at, might be simple, but also might be complex. What graph-based alerting is doing is moving that complexity and saying, we want to try to reduce our problem to something you can reason about with a threshold. So rather than having a complex rule, you have a powerful query language. So you have powerful collection. So you make sure that you transform your data into something you can reason about on a graph. And no real need for unit testing there as long as you have unit testing of your query language. But you probably have that anyway.
Okay, I think we're at the end now.
Can I say one more thing? Yes. I am long-winded, I know. But this was actually, I had a bunch of learnings of things we picked up along the way. But the most important thing I actually have to say is the one that we haven't solved, and to the best of my knowledge is not really solved yet. A lot of us are still talking about scaling monitoring, as in scaling collection and scaling graphing. I want to give you an idea of what comes after that, because it's not over. After 100 million time series, the next problem that comes is a human one, not a machine one. It's discovery. Your machine has no problem reasoning about 100 million time series. You can remember them all. But as a human, trying to find out what you have in your monitoring system and what to drill down in, that's really difficult. Building a UI that can give you an overview of this much data is really difficult. Not because the machine can't handle it, but because your users, the ones who are consuming it, can't. And this is, to the best of my knowledge, a somewhat unsolved problem. There are some promising solutions of upcoming companies bringing in anomaly detection. I don't know if there's anomaly detection in the open source world yet. And it looks promising that machine learning and anomaly detection can help us focus in on this huge amount of data. But the people I've talked to so far, this is what comes next. This is the next scaling problem for us. Searching this data, finding what is interesting. We'll see what the solution will be. Thank you.